What I'd like to do is to show the role that the Lyman series lines, and by that I mean Lyman alpha, beta, and gamma, on various topics, in particular stellar stars, exoplanets, interstellar medium, deuterium, galactic chemical evolution, etc. So let's see how this plays out. I'm basically starting with what I understand as the capabilities of Arcus, namely X-ray spectroscopy with a resolution of 3500 approximately, far UV spectroscopy, the entire range of 970 to 1350 angstroms with 13.6 kilometers a second spectral resolution, and most important, 6 times higher sensitivity than was capable with FUSE. Both capabilities are simultaneous. They're uniquely important for studying variable sources. And the other thing I mentioned is the 7-day orbital period of Arcus basically means long duration, uninterrupted observations, and very important for this, what I'm going to say below is low geocoronal emission. Okay, so let's look at the Lyman lines. Hubble could only observe Lyman alpha. FUSE could only observe with low sensitivity the higher lines in the Lyman series. I list the lines on the right: Lyman alpha, beta, gamma, delta. Delta may not be observable by Arcus, but the other three should be. Arcus has a spectral resolution of 14 kilometers a second, which, given the separation between the deuterium and hydrogen Lyman lines of about 81 kilometers a second, means that we can resolve the deuterium from the hydrogen lines. D to H has a ratio of about 1.5 times 10 to the minus 5 in the local interstellar medium. So as a result, the optical depths at line center for the hydrogen lines and the deuterium lines are very different. And if one can analyze alpha, beta, gamma, there's another wide range of opacities that one can sample. And also mentioned high orbit suppresses geocorona emission, not just at Lyman alpha, but also at Lyman beta and gamma. Okay, Lyman alpha. For many problems, it's very important to measure the intrinsic emission of the Lyman alpha line and that component of the Lyman alpha emission that's due to interstellar absorption. So what's shown here is a Rogues diagram of a number of objects observed by Hubble. Lyman alpha, solid black is the observations. The thin black line is the essentially reconstructed intrinsic Lyman alpha line. To go from the observed to the intrinsic is an important piece of work that we've been working on for the last 15 years. I think we understand most of how to make that correction, but it really needs to be tested. And since we've only done it with Lyman alpha, it'd be really important to look at Lyman beta, maybe even Lyman gamma, do the same kind of reconstruction and see if we're making sense with Lyman alpha. The very different opacities between the Lyman lines makes this feasible. I just want to point out that in some short lines of sight where the interstellar absorption at Lyman alpha is relatively weak, the difference between the observed and the reconstructed line profiles are relatively small. In other cases, the difference is huge. Okay, onwards. I think many people immediately recognize the importance of the Lyman lines for stellar activity and transients. Let me just point out what may be obvious to many people, namely Lyman alpha is the brightest emission line for G stars like the sun. It is also as bright as all the other emission lines for M stars, which are really important host stars for exoplanets. And measuring the intrinsic Lyman alpha flux is essential for these studies. Okay, so this is coupled into the interstellar absorption part of my talk. And the analysis of Lyman alpha and Lyman beta would be a great test for how it is that we're doing this intrinsic reconstruction. Simultaneous X-ray and far UV spectroscopy will supply unique data for studying transients, including stellar flares, coronal mass ejections, activity indicators. I'm not going into any details on this. There are talks by Austin and Shkolnick that are very important on this. And also, I think it was pointed out that this kind of science is mostly guest observer science and not part of the science team. Previous studies of X-ray and UV emission from stars, for example, or exoplanets have required difficult coordination and scheduling issues between several spacecraft. That problem is now resolved. The other thing I want to point out is that the far UV spectrograph on Arcus will include a number of lines in the 97 to 120 nanometer region, lines of carbon-2, carbon-3, silica-3, helium-2, oxygen-6, iron 18 and 19, in addition to the usual set of emission lines that one sees in Hubble spectra. Okay, just to whet your appetite, I show fuse spectra of dwarf stars. This is a composite of many different dwarf stars observed by fuse. There also is a companion paper by Dupre and collaborators on giants and supergiant stars observed by fuse. I do want to point out that H beta and H gamma are seen in these spectra, but the flux that, sorry for that, the sensitivity of Arcus will be approximately 6 times that of fuse, so we're going to obtain much more sensitive spectra. Okay, importance of Lyman lines for exoplanet atmospheres and mass loss. This is another major topic, but let me just mention 2 aspects of it. One is photodissociation in the atmospheres of exoplanets. For example, water and methane is driven largely by Lyman alpha, whereas the photodissociation of CO2, CO, H2, and N2 is driven by shorter wavelengths. So if you look at the figure on the right, this basically plots what fraction of the dissociation of a given molecule is due to radiation at wavelengths, at shorter wavelengths up to a specific wavelength. And what you'll see in the case of water, the second panel, is water essentially shorter wavelengths than Lyman alpha play no role at all in the dissociation of water. Lyman alpha totally dominates the dissociation of water. Therefore, we have to measure the intrinsic Lyman alpha flux of a star in order to understand photochemistry of water. The same thing is methane, the bottom panel. On the other hand, CO, CO2, H2, for example, panels 3 and 1 are basically photodissociated by radiation shortwards of Lyman alpha, and this is where Arcus can be very important. There are 3 different types of lines shown here: dashed line, a gray line, and a solid line, and that's for different types of stars. Epsilon area strong far UV emitter, GJ 581 a weak far UV emitter, and the sun. And then there's the whole question of deuterium and galactic chemical evolution. D over H, that number ratio in the gas phase, which is what we measure, varies across the galaxy due to many effects. Estration, namely the conversion of deuterium to helium in stars, the removal of deuterium from the gas phase onto dust grains, patchy infall of near primordial gas, incomplete mixing, and who knows what else. Okay, what's shown on the right is a figure from a very recent paper by Friedman, compiling together the D to H ratios measured primarily by Lyman alpha for the stars, the targets within 100 parsecs or so of the sun, and that's the solid data, black data. Red data is new observations measured by Friedman. And what I want to point out is within about 100 parsecs of the sun, there appears to be a pretty much constant value of d over h, but this is based entirely only on Lyman alpha data. The inclusion of Lyman beta as a test of how accurate Lyman alpha is would be very helpful. And the main uncertainty in these measurements is the column density of neutral hydrogen. Measuring the column density of neutral deuterium is by far easier, much easier than hydrogen. Okay, so here's where Lyman beta can play an important role. And I show here essentially the dust is measured from, dust intensity is measured from the sun, and you see within 100 or 200 parsecs is the local bubble, very low density material, very low dust, and then clouds of higher dust around it. And this may explain why it is around 100 or 200 parsecs from the sun, we begin to see a very wide variation in D to H, and we'd like to know why.
Thank you. Dennis, do you have a conclusion slide? Perfect.
Conclusions. Okay. The combination of X-ray and far UV spectroscopy will make Arcus a major contributor to our understanding of stellar activity and transients and lots of other topics. I hope that's well understood at this point. The analysis of the fluxes and spectral shapes of the Lyman series lines, Lyman alpha, beta, and gamma, will play a critical role in a number of these topics. And the Lyman beta and gamma observations will be done with much higher sensitivity than FUSE, and of course, Hubble couldn't do it. The 7-day orbit of Arcus is essential for minimizing geocoronal emission at the hydrogen lines and providing long, uninterrupted observing programs. And a final point, suggestion, encouragement to the Arcus development team, and specifically to Kevin France, is please provide the highest feasible spectral resolution, throughput, and line profile shapes for the Lyman lines and other lines in the far UV.